Alright, for video number 1 here, I'm just going to finish up this problem from class yesterday dealing with a horizontally fired dart. So I'm firing the gun from 1.5 meters above the ground. We're firing it parallel to the ground, and the dart landed 5 meters from my feet. And the question was, what was the speed of the dart when it exited the dart gun? So we talked yesterday about things you would need to recognize in the problem. Obviously, we're doing projectiles right now, but in the future, if there are many other physics topics being covered, you have to recognize this is a projectile situation because you have an object moving through the air being affected only by gravity. As soon as you know you have a projectile situation, you know that the acceleration is only from gravity and only on the y-axis. So we're going to say the acceleration on the x-axis is 0 meters per second squared, while the acceleration on the y-axis is negative g. The other important thing you need to recognize in a problem like this is in the setup, I tell you that it's fired parallel to the ground. And so what we recognize there is that for the velocity, the initial velocity I should say, the j hat portion of that vector is going to be 0 meters per second. So our y-axis initial velocity is 0 meters per second because we are not shooting the dart up and we are not shooting the dart down at all initially. If you want to think about this another way, if we fired this dart in this situation but there was no gravity, the dart would just continue to move along the x-axis. So that's where we're getting that initial velocity on the y-axis equal to 0. The next thing I suggested you do is to draw a picture. Now, I also mentioned yesterday that this picture could be done in conjunction with step 1. So you can go ahead and start drawing the picture and thinking about the ideas of what is occurring in the problem as you go along. Important things to have here, because this is kinematics, is you need to have number lines. And so that's going to allow us to mark our positions. But because we're talking about two-dimensional motion, and specifically a two-dimensional type of motion referred to as a projectile, we need to have two different number lines. One for our y-axis, one for our x-axis. So this is the picture we came up with in class yesterday. The initial velocity is marked here with a vector. And then, if you weren't there yesterday, I just pointed out, I personally like to throw in the parabolic path of the object as well. And so one mistake that I see a lot with beginning physics students is that first they'll want to try and make a third position vector, finding the displacement from, say, here down to here, and okay, yes, that is the ultimate displacement of the dart. Actually, I missed. It should be on top of that dart there, but it's not terribly useful to us. There's not much we would be doing with that displacement. The displacement on the x is useful, the displacement on the y is useful. We can put that into physics formulas, but there just isn't much we can do with that overall displacement unless that's what is being asked of us. So be a little bit leery if you find yourself doing something like that. All right, so I said probably the biggest thing you have to do next is really organize this information. Beginning physics students, if they're making mistakes with the projectiles, one of the things I notice over and over again is that the information isn't organized. And this is really important because we're talking about motion on the x-axis, motion on the y-axis. They're independent of each other. You can't mix them together. So if you don't have it organized and know what's what, you end up putting stuff into formulas together that just shouldn't be put together. So, biggest culprit I'll see is x-axis position information put in with gravity as the acceleration from the y-axis, and that's a big no-no. I also pointed out yesterday, hey, if you use the projectile equations that I have, the acceleration on the x is going to be 0, acceleration on the y is negative g. I already plugged that into the projectile equations that I gave you 2 days ago in class. So I've also put in here v initial on the y-axis as 0 meters per second, as we discussed earlier, because this is a horizontal launch projectile. All right, so you can also take a look at all the other variables here. It's just kind of stuff that I took from my picture and listed out just to make sure I'm not messing up what's on my x and what's on my y. The one thing we did next is we said, okay, well, we're supposed to figure out then what the initial velocity of this dart is. We already know initial velocity on the y is 0 meters per second, so I'm going to go to the x-axis. And when I go and look at the x-axis, there's only one projectile formula that's any good, this guy. X final equals x initial plus voxt. When it's a projectile, because acceleration on the x is 0, this was the only equation we were left with for the x-axis for a projectile. Go through that, and you look and you see you have another unknown, time. And that's where we run into a problem. You can't use the x-axis to get time here because you just don't have enough information. However, because time on the x-axis is the same as time on the y-axis, we can go ahead and use the y-axis to figure out the time. And the best way to do this is going to be take this formula and we're going to plug in the values that we know. So we've got in our problem that y final is 0. We've got y initial, we have y initial as 1.5 meters. We saw that VOY, we said that was 0, and that's a big deal because if you didn't know that, you would also have another unknown and you wouldn't be able to solve this. So if you didn't recognize VOY as 0, you're not getting anywhere with this problem. All right, plug in, I'm going to use 10 for G here if you're okay with that, 10 meters per second squared. I hope you're okay with it because I'm alone in this room making this video right now and you're just going to have to deal with it. But putting in 10 for G, I get negative 5t squared when I multiply by 1/2. Okay. So now I've got negative 1.5 meters equals negative 5t squared. And so we're going to get, if we divide both sides by the negative 5, we're going to have a number that is going to be negative 0.3 equal to t squared. I'm going to take the square root of that. Oops, whoops, goofed up. Lost my negative when I divide by negative 5. Take the square root of both sides, and let's quickly do this. By the way, one of my other classes showed me this app. It's fun. So let me pull it up here. If you didn't see it in our class, oh hey, I'll install that later. Okay, great. Hey, there's my passcode. That was perfect timing, iPad. Alright, so neat little app here called Calculator if you haven't seen it. And I'm just going to type in 0.3 and calculate. Boom, 0.547. So I'm going to go here and we get t equals 0.55 seconds. That was a free app. Nice, quick, easy way to do some calculations if you use it properly. All right, so we have the time, and now what we're going to do is go back up to our previous formula. So we have the time. Plug that in there. VOX, got our x initial, and that's equal to our x final. X final was, what do we have, 5 meters? Sounds right to me. Mr. Mulvin, that sound good to you?
It sounds excellent, Mr. Schramm.
Alright, so we're going to do 5 divided by the 0.55 seconds.
Indubitably.
Don't think it likes my handwriting. Yeah, close enough. But anyways, we get VOX to be about 9.4 meters per second.
Fascinating.
And that is the starting velocity of the dart because there was no initial velocity on the y-axis, and we are done.